Welcome to today's Explainer. We're jumping right into the invisible quantum mechanics that literally create every single color in the world around you. If you've ever just, stopped to marvel at a bright blue sky, a really vibrant gemstone, or even the glowing screen you're staring at right now, well, you're actually witnessing one of the most fundamental, fascinating laws of physics in real time.
So let's kick things off with a simple question about something you probably see every single day. Why exactly does a regular piece of fruit, like a shiny apple, look red to your eyes? I mean, we usually just accept that red is a built-in property of the apple itself, right? Like the universe just painted it that color? But the truth is actually way more dynamic, and honestly, a lot stranger than that.
Section 1. The Quantum Secret of Color. To really answer that question about the apple, we have to zoom way past the skin. We need to shrink all the way down to the microscopic atomic level. Because this is the exact spot where quantum mechanics, which is the weird set of rules governing tiny particles like electrons, crashes right into electromagnetism, the science of how light travels.
Think of the electrons orbiting every atom in that apple's skin as incredibly picky eaters. When white light, which remember contains all the colors of the rainbow, hits the apple, these electrons start feeding. They happily absorb the high-energy blue and medium-energy green light photons. Those photons just vanish, their energy turning into a tiny, completely unnoticeable bit of heat in the fruit. But they outright refuse to eat the red light. They literally just cannot absorb that specific energy. So the red light bounces right off the apple and smacks straight into your eyes.
Section 2. Electrons and quantum leaps. But wait, where do those colored light packets come from in the very first place, before they ever even hit our apple? To figure that out, we need to look at how electrons behave inside an atom when they get energized.
This whole thing happens in 4 distinct steps. You know that every atom has electrons orbiting a central nucleus, and these electrons live in very specific shells or energy levels. So, step 1. When an atom gets hit by energy, like heat from a flame or light from a bulb, an electron gets excited. Step 2. It performs a quantum leap. It jumps up from its natural home shell to a higher, more energetic level. But here's the catch for step 3. Electrons are, well, naturally pretty lazy. They really don't like being excited, and they desperately want to just go back home. So they quickly drop back down. And finally, step 4. To get back home, they have to get rid of that extra energy they just picked up, which they do by spitting out a tiny glowing packet of light called a photon. Now, the exact size of that electron drop perfectly dictates the color of light that gets created. Remember, light travels as a wave. If the electron makes just a small drop to get back home, it releases a low-energy photon. Low energy translates to a long, stretched-out wavelength, with the distance between the wave peaks measuring about 700 nanometers. To our eyes, that long wave looks red. On the flip side, a big drop releases a high-energy photon. High energy means a short, fast, compressed wavelength of about 400 nanometers, and that creates violet or blue light.
And this relationship isn't just a theory, it's defined by a fundamental equation in quantum electrodynamics. E equals h times c divided by lambda. Let's break that down into plain English. E is the energy of the photon. The h is a fixed mathematical number called Planck's constant. The c is the speed of light, and lambda, that little symbol at the bottom, is the wavelength. Because the wavelength divides the energy, this math proves that energy and wavelength are exact opposites. A massive energy jump creates a tiny, short wavelength, and vice versa. It's really that simple.
Section 3. Atomic fingerprints in action. Because every single chemical element in the universe has a completely unique atomic structure, the specific distances between their electron shells are rigidly fixed. They basically act like a visible, colorful atomic fingerprint. If this weren't true, every single object in the universe would just look the exact same color. Think about precious gemstones for a second. Rubies and sapphires are actually super similar types of crystal gems, but a ruby happens to trap tiny amounts of chromium atoms inside it. The electrons in chromium have specific energy gaps that absolutely love to absorb green and blue light, leaving only red to reflect back to us. A sapphire, meanwhile, traps iron and titanium atoms. The electron gaps in those elements absorb red and yellow light, leaving only that stunning blue to reflect into your eyes. So the color you see is literally the fingerprint of the trapped atoms. We can actually see this happen right before our eyes in a chemistry lab using a flame test. This technique was pioneered by 19th century scientists like Gustav Kirchhoff and Robert Bunsen. By burning different materials and observing the distinct colored flames, they were the very first people to realize that elements have completely unique light fingerprints. When you heat up a piece of copper, the fire forces its electrons to jump and fall, emitting photons with a wavelength of exactly 520 nanometers. That produces a bright neon green flame. But if you heat up the element strontium, its unique electron gaps force a totally different drop, emitting photons at a 650 nanometer wavelength, which burns a brilliant deep red.
Section 4. Real-world tech. Now this isn't just a neat chemistry trick for the classroom or some dusty piece of history. Mastering these precise electron quantum leaps is the exact science that powers our modern technology and completely guides our exploration of the universe.
The crucial point here is that we harness this quantum mechanics every single day. Take the screen you're looking at right now. Engineers use highly specific materials, like gallium nitride, inside LED displays. They physically engineer the material so that when electricity hits it, its electrons jump the exact right distance to create the perfect, brilliant colors of light for your phone screen. And honestly, what's even more amazing, astronomers use this exact same principle to look at stars billions of miles away. Because they know exactly which electron jumps create which specific wavelengths of light, they can look at the color of a star and map out exactly what gases it's burning without ever having to leave Earth. It's like reading a barcode from across the galaxy.
Section 5. The limits of human sight. All right, here is the most mind-bending part of this entire explainer. Despite all this incredible color and energy constantly bouncing around the universe, we are actually totally blind to almost all of it.
The entire rainbow of visible light that we can see, every sunset, every painting, every eye color, exists in an unfathomably tiny, narrow band of the electromagnetic spectrum. We can only process light waves that measure between 400 and 700 nanometers. Anything shorter than that, or anything longer, is completely 100% invisible to us.
The only reason we even see this specific slice of reality is pure biology. Human eyes evolved specialized cells called cones. You can kind of think of these cones as highly tuned biological antennas. They're biologically engineered to perfectly catch the specific energy wavelengths between 400 and 700 nanometers that are being released by electron drops right here in our earthly environment, and absolutely nothing else.
Which leaves us with this really incredible, provocative thought to take away today. If human biology had evolved just a tiny bit differently to catch different energy gaps from different electron jumps, what would the invisible world of radio waves or X-rays look like to us? Just imagine the invisible colors bursting out of your Wi-Fi router or the nearest hospital, painting a universe of vibrant, unseen light right in front of you. Thanks for joining me for this explainer, and keep looking at the world just a little differently.